Welcome to the training for Mechanical Science Fundamentals, STEAM Systems. The average time to complete this training is estimated to be 20 minutes. After you have completed this portion of training, you will be directed to the next training lesson in the series for further instructions. These are the objectives for this course. Steam systems at SRS provide high-quality, low-moisture content steam at the required pressures and flow rates to systems and components, while also providing a positive means of preventing the spread of radioactive contamination. The steam systems supply heating steam to ventilation system heating and humidification units, component heaters, heating steam for the various process systems such as evaporators, and other miscellaneous loads. Most steam systems have many components in common. The primary major difference is the heat source to the steam generator. In this picture, the heat source is a reactor. On site, we use coal, oil, or biomass boilers. The steam supplied to LWO is produced by the site powerhouse. Site steam headers distribute steam to the various areas, including the tank farms and DWPF. This drawing shows the various components that make up a typical steam supply system. Steam is supplied by the steam generator and distributed to the various steam loads. On a closed-loop system, the used steam is routed to a condenser, where it is condensed back to water and then supplied back to the steam generator by the condensator feed pumps. The steam pressure supplied to the loads is reduced to the appropriate pressure by pressure-reducing stations. A couple of terms related to steam systems. Quality is the mass percentage of steam in a steam-water mixture. Steam with a high quality contains a low percentage of moisture. Carryover is the water which accompanies steam exiting a steam generator. Moisture carried over by steam is in the form of water droplets. Carryover is minimized by the use of moisture separators and level control in the steam generator. A steam generator is typically a shell and tube heat exchanger. A site steam generator uses 260 psi heating steam. The heating steam enters the steam generator, flows through the tubes, and returns to the 260 psi system. The heating steam never physically comes in contact with the water being boiled. The feed pumps continuously supply the shell of the steam generator with feed water through the feed water inlet. As the feed water flows around the outside of the tubes, the steam inside the tubes gives up heat to the feed water. There is sufficient energy in the high-pressure steam to boil the low-pressure feed water. In the steam generator, steam may carry liquid droplets along with it. Before leaving, the steam is forced to flow through mist eliminators that remove any entrained water droplets from the steam prior to exiting. Removing moisture reduces the erosion and damage to downstream components. This is typically done by one of two ways. One method is using a set of baffles which force the steam to rapidly change direction. The heavier water droplets cannot make the direction changes as easy as the steam and fall back into the steam generator. The other means is by using a tightly woven stainless steel mesh. The water droplets collect on the mesh as the steam flows through and falls back into the steam generator. A steam header is simply a series of piping and valves. They are used to transport steam produced in the steam generator to be distributed to various components for use. Steam headers incorporate reducing stations to provide the correct steam pressure to systems and components. Steam headers will also include control valves, drain valves, steam traps, and manual valves used for system startup and isolation. A pressure reducing station is installed in steam systems to reduce the steam pressure to downstream loads. Reducing stations have one or more pressure control valves, PCVs, and safety valves. Some PCVs maintain the downstream pressure at a set point which is controlled by a pneumatic operator. Other PCVs are mechanical spring-loaded diaphragm type pressure reducing valves, as shown here. The safety valves protect the low-pressure piping and components from overpressure. The safety valves are located downstream of the PCVs. Drip legs consist of piping attached to low points in the steam system. They collect and remove the condensate that forms in the steam lines. Each drip leg has a steam trap, an isolation valve, and a blowdown valve. The blowdown valve is used to drain condensate from the line during warm-up of the steam system. After the initial condensate is drained, the blowdown valve is shut and the steam trap is placed in service by opening the inlet isolation valve to automatically remove condensate during normal operation. flash tank allows hot condensate to flash to a vapor. When pressurized hot water enters a low-pressure tank, some of it will flash to steam. The steam is typically used to supplement a low-pressure steam system, for example 20 psig. This process increases the steam efficiency by using heat that would normally be wasted. The remaining condensate is cooler due to giving up the latent heat of vaporization to the steam. The purpose of a condenser is to remove heat from a vapor and change it to a liquid. Steam enters a condenser and flows around the tubes. Cooling water flows through the tubes. Heat is transferred from the steam to the cooling water inside the tubes. Removing the latent heat of condensation causes the steam to condense. The condensate is then returned to the steam generator for reuse. Air and other non-condensable gases in the steam system can reduce efficiency and interfere with proper operation. When in the condenser, these can blanket the tubes and prevent condensing of the entering steam. When in piping, it can interfere with proper warm-up of the piping during startup. In the feed and condensate pumps, it can cause air binding of the pumps and reduce or prevent flow. Air and non-condensable gases are removed by steam traps during startup and by the condensate hold tank during operation. Condensate in steam lines can cause water hammer and damage steam-operated equipment. For these reasons, steam traps are used to remove condensate from steam lines during normal operation. Steam traps are installed at low points to remove the condensate before it causes equipment damage or personnel injury. A steam trap must also be able to remove air and non-condensable gases from the piping during initial startup of a steam system. Steam traps are classified by construction and operating principle. One of the oldest types of traps is the bucket trap. The bucket steam trap uses a valve and bucket arrangement. Condensate enters the trap body and causes the bucket to float. The bucket is connected to the valve, which is closed when the bucket floats and is open when the bucket sinks. Condensate continues to flow into the trap body until the trap body fills and overflows into the bucket. When the bucket is full, it sinks and the valve opens. Steam pressure forces the condensate in the bucket out of the trap through the valve. Once the bucket is empty, it again floats and shuts the valve. In the inverted bucket steam trap, the trap contains an inverted bucket linked to the discharge valve. The opening force is provided by the difference in density between steam and condensate. When the steam enters the upturned bucket from below, it causes it to float. When enough condensate enters the bucket, forcing the steam out of the vent hole, the bucket sinks, opening the valve. When the condensate has been drained from the line and steam enters, the bucket again floats, shutting the valve. A ball float steam trap consists of a valve that is operated by a ball float mechanism. When the trap is in operation, steam and water enter the trap. The water, which is heavier than the steam, collects in the bottom of the trap. As the water level rises, it lifts the float, which causes the valve to open. The condensate is blown out of the trap by steam pressure until its level drops to a point where the ball float closes the valve. The valve and float mechanism is designed in such a way that the valve will close before the condensate level gets low enough to allow steam to escape. A thermostatic steam trap is one that operates based on a temperature change. A bellows type steam trap consists of a bellows and valve. The bellows is filled with a volatile liquid that flashes to vapor or condenses with temperature changes. When hot steam is in the trap around the bellows, the liquid in the bellows flashes to vapor and closes the valve. As cooler condensate enters the trap around the bellows, the vapor condenses, opening the valve, allowing condensate from the steam system to flow out. The thermostatic float and bellows is a ball and float trap with a bellows vent valve installed. The float portion of the valve operates the same as the ball and float. The vent valve operates by expansion and contraction of the bellows element. When the bellows is cool and contracted, any air or non-condensable gases that enter the trap during normal operation will collect at the top of the trap chamber. As the thermostatic element cools, it contracts, allowing air to be discharged. As steam reaches the trap, the bellows element fluid vaporizes and expands the bellows to close the vent valve. In a thermodynamic disk trap, when condensate is present, the disk is pushed off the seat and condensate flows out. A small bit of hot condensate goes around the edges of the disk and above the disk. When steam is present, it heats up the disk, and the condensate above the disk vaporizes, shutting the valve. When condensate is again present, it cools the disk and the steam above the disk condenses, allowing the condensate to push the disk open. Similar in concept to the thermodynamic disk, the impulse steam trap works due to a small amount of condensate flashing to steam when hot. In this case, the disk is attached to a small piston that is contained in a tapered cylinder. Condensate pushes the piston upward, and a small amount of condensate flows around the disk in the tapered cylinder. As higher temperature steam comes in and heats the cylinder, the condensate above the disk flashes to vapor, forcing the piston downward, shutting the valve. As the condensate enters and surrounds the cylinder, the steam above the disk condenses and the cycle repeats. This type of trap makes a characteristic clicking sound that can be heard by use of a stethoscope. If an impulse steam trap is stuck open, indicated by steam blowing out the discharge line, or stuck shut, indicated by nothing coming from the discharge line, the stethoscope can be used to check for clicking sounds to determine which trap is malfunctioning. Just like any other mechanical component, steam traps are susceptible to failures. Foreign materials can collect in the trap, or trap components may corrode. One type of failure is a stuck open valve. This condition is indicated by steam blowing out of an in-service trap. If a steam trap is observed in this condition, it should be reported immediately. Besides being a waste of steam, it can be hazardous to personnel, and continued use of a trap in this condition could cause damage to the seating surface of the valve. Exposure to live steam under pressure can cause severe burns, steam cuts, lung damage, and eye damage. Another failure is a stuck closed valve. This is less common and harder to detect. It is indicated by a lack of condensate coming from the drain line of an in-service steam trap. If this condition is suspected, it should be reported immediately because it could prove dangerous due to condensate buildup leading to a potential for water hammer. LWO receives steam from the site steam system, which is distributed across the site at 325 pounds per square inch gauge. It is distributed to the different areas where reducing stations reduce the pressure for their various loads. On the steam headers, steam traps are located on low points to collect any condensation and discharge it to drains. The steam line piping is slowly warmed up progressively while draining condensate from the drip legs using blowdown valves. To start, all blowdown valves are opened and the traps isolated. The bypass valve for the main steam valve is cracked open to allow a small amount of steam flow into the piping. As the line starts to warm up, condensate will issue from the blowdown valves. When all of the condensate is drained and only steam issues from the blowdown line, shut the blowdown valve and place the trap on service. Continue the same process on downstream traps until all line traps are in service. Slowly open the main steam valve and shut the bypass valve. Improper steam line warm-up can result in condensate in the steam pipes causing water hammer. Water hammer is very dangerous to personnel and components. Many components and steam systems have installed strainers, such as Y strainers, to remove foreign material and corrosion products. Strainers should be cleaned and inspected on a regular basis. Improper steam valve operation, for example too fast open or shut, can result in pressure surges, pipe whip, water hammer, and failure of steam system piping and components. Exposure to live steam under pressure can cause severe burns, steam cuts, lung damage, and eye damage. Extreme care should be taken to report and repair any and all steam leaks and always wear appropriate PPE. Steam line and equipment explosion can result from improper steam valve operation, water hammer, failure to maintain lines and equipment properly. When operating around steam generation and steam-powered equipment, it is likely to be in high noise levels and high heat levels. Proper PPE shall be worn in all actions taken to prevent heat-related illnesses. Steam system components that do not have insulation are very hot. Some components, such as steam traps, are purposely not insulated in order for them to operate properly. Extreme care shall be taken when working around uninsulated equipment. Failure to wear proper PPE and appropriate work clothing will result in severe burns.